Okay, so let us start now. By the way, just a reminder, do you remember this four? Because in calculus, you have heard about the min-max theorem, but you didn't know about metric spaces back then, probably. So how did they phrase this theorem for you in calculus? You remember that? The function was defined in this way. If f is from a closed interval, yes, to R, then this, and f is continuous, it actually attains its max and mean. That was the max-min theorem. The max-min theorem in calculus was told you in this way. If f is a function defined on a closed interval from a to b, then f attains its, and it is continuous, it attains its maximum and minimum. Okay? So the one we have shown here is that if the domain is a compact metric space, then the theorem works. And then do you remember we learned that this one is a compact metric space because it is closed and bounded and it is in Euclidean spaces. So this theorem that you learned in the calculus is a very simplified version of this more generic theorem. Yes? I just want you to know about that. Okay, so now more or less one topic is left here, and that is an extremely important one. And I have given you some exercises because sometimes it is not that easy. This is an epsilon delta definition, and that's the notion of uniform continuity, which is important. So this is the more or less the last topic of one big theorem. So what is the meaning of uniform continuity? Let me explain it here for you. So far, if I give you a function from a metric space to another, so let us write. You remember the setup for just continuity. This has an adjective with it, uniform continuity. But let us go back and review continuity itself. So if x and dx and y and dy are metric spaces, and then do you remember what was the setup? A is a subset of x, and then f is a function from a to y, and then p is a point in x. We say that f is continuous at p. F is said to be continuous at p if, do you remember, for every epsilon there exists a delta such that for all x, if for all x in A, the domain, if the distance between x and p on the x side is less than delta, then the distance on the y side between the values is less than epsilon. Yes? That was the definition of continuity at a point P. But now, if I want to tell you f is said to be continuous, if I want to take it off, can you fix it for me? Okay, so because I want to clean this one now. This was the usual definition. But now f is said to be continuous. Instead of this one, I want to write on A. Yes, if what happens? Continuous on A if it is continuous at every point. Is that right? It means for every P in A, this happens. Is that right? Okay, then what? For every P in A and for every epsilon greater than 0, there exists a delta. This delta in principle depends on two things. Can you tell me? Because we have two universal quantifier before this existential quantifier. It tells you that for every P that you choose and for every epsilon that I give you, you can find a delta. So this delta depends on, yes?
P and epsilon.
P and epsilon. Do you agree? So this depends in general on P and epsilon. Okay? This is the meaning. Okay, but now, if I can find a delta that works for every pair, then that is the notion of uniform continuity. So now I want to define what I have written here. So it is 10.7. So 10.7. What setup I have? I have the same setup. I would say that F is said to be uniformly continuous on A if, so what I say is like this, for every epsilon greater than 0, there exists a delta greater than 0, so that for every pair of x and y in A, if the distance between x and y on the x side is less than delta, then the distance between the values on the y side is less than epsilon. Okay, so this is the importance, you know, somehow this dependence on the point has moved for later, okay? So you see, one point I fixed, and for every point it should work. But now, what I am doing, I am choosing any epsilon. I want to know that if there is a delta, so that for every pair of elements that I choose from A, this guarantees that one. So this is the definition, okay? So now can you tell me in this case, delta belongs on what? Delta belongs only on epsilon. Sorry, depends on epsilon, but not x and y. So here, if you want to prove continuity, you have to prove that for every epsilon there is a delta, so that it works for every x, but p is fixed first. So this delta depends on p and epsilon. But in this case, delta depends only on epsilon. So this is the definition of uniform continuity. Is that clear? It's not very clear, I know, but I will explain it a little bit. For example, I don't know if I can give a good picture example for you. So let me give it here. I hope that I can. So let us say that this is a function of this form, but I just want to look at this function from here onward. It continues. So what I am trying to say is that if you have a function like this in the normal 2D dimensions r squared, this is not uniformly continuous. It is, what is the domain of this function? The domain of this function starts from here and goes up to infinity. This is the domain of my function. I am telling you that this function is not uniformly continuous on its domain. Why that is the case? This means that, let me, for example, fix a length on the y side. Okay, so let me fix this length on the y side. Let me call it L. This is the tolerance that I might have in the y values. So if I want to be within this tolerance, for example, I cannot choose two values, one here and one there, yes? Because when I map them, it will go beyond this threshold. If I ask you where I can be so that it is mapped within this tolerable threshold that I want, where should I go? So I go backward. I go here and I go here. I say that, okay, if you are within this threshold, yes, it is guaranteed that you go in here, yes? So it means this one, imagine this is your delta. So the threshold of the length on the x-axis that will give me this much threshold on the y-axis is at most this much. Okay? But the point is that this delta, I cannot give you one delta that works everywhere. Why? Because if I take this one, I keep the length the same, but I move it here. Okay, so let us see what happens now. So still, the threshold on the y that I desire is still L. But do you think that this delta, this threshold of the x-axis will give rise to this one? No, because if you want to engineer that, because of the steepness here, you need to adjust your delta to a smaller delta, you see? This delta, let me call this delta 1, this is delta 2. Delta 2 should be less than delta 1. So it means that if I want to achieve this threshold on the y-axis, I cannot fix a delta for you that works for every case. Do you agree? Because if I fix this delta for you, it works if this line segment is here, but if this long segment is a little bit higher, that delta does not work because you see that I have to shrink the delta to achieve this goal. Do you understand that? So this means that this is a non-uniform continuity. It is continuous, but it is not uniformly continuous because even though I am not changing epsilon, the threshold on the y-axis is the epsilon one. But to achieve that threshold, depending where this is, I have to adjust deltas. So there is no one universal delta that works for every case. Do you agree? So, why? Because if I can go farther and farther, so I have to fine-tune my delta over and over again. But how many points are there? There are infinitely many. So I cannot give you one delta eventually that works for every case. Is that right? But let us imagine, can you imagine one picture that it is uniformly continuous now? It's not hard to imagine. If you understood this, yes?
Y equals to x.
Y equals to x is a very simple one. Yes, but let us y equals to square root of x, for example. So instead of having this behavior, let us have a concave down behavior. Okay, so for example, let me just do it like this. Something like that. Okay, this is suddenly become, so here is the domain again, so the domain is again goes to the right. But now look, if I take this length here, the delta that I want to adjust is this much. This is delta 1. Okay? But if I take this here, what happens to my delta? Do you think the threshold of delta increases or decreases in this case? Because in the case that it decreases, I am in trouble because I cannot give you one delta that works for everything because the one, the ideal one is at infinity, but I will never reach at infinity, yes? So if I give you this, the threshold for delta will be wider this time. Okay, do you see that? And then what happens? If you want to give me a delta, that works for threshold of L, which delta you give me? The first one. The first one will work for everyone after that. You understand that? So this behavior is uniform continuity. This behavior is non-uniform continuity because both of them are continuous, yes, on the domain. Is that understandable? Okay, so which one implies the other one? Do you think that is a very important question of this course now? So do you think if I give you a function which is uniformly continuous, is it granted that it is also continuous? Do you agree that this is more or less trivial? And that is the idea of the, I have written all these epsilon deltas here for you. And this one is this theorem. Uniform continuity implies a continuity. Yes, do you agree? If a function is continuous, do you see why? If a function is continuous, do you agree? If it is uniformly continuous, it means that you can find a delta that works for your epsilon independent of the points. So it also works for your point. Yes? So it is like this. You know, I have to remember. So let us say that L, X, and Y means X loves Y. Yeah? Okay, so what is this? What is the meaning of this sentence? So what's the meaning of this sentence? How do you read it in English if I am right? Yes?
For every X, there exists a Y that person loves.
There is a person that everyone loves him or her.
Oh yeah, okay, yeah.
Yeah, that's the meaning. There is a person that everyone loves him or her. Okay? But now, what is the meaning of this one? This is hard to find in human societies. Yes. But this one is more or less natural. What is the meaning of this? Yes?
That everybody has somebody that they love.
Has somebody to love. Yeah, this is very hard to find in this world. Yes? But then one of them they are not equivalent. You can feel it. Okay? These are not the same sentences. Yes? But one of them will definitely imply the other one. Which one? So you see, they are not equivalent. But which one implies the other one? If one of them is true, the second one is guaranteed to be true. Yes?
The first implies the other.
Yes. If there is a person that everyone loves him or her, it means that everyone has someone to love, and that's that person. Yes? So this means that this is in this way correct. But it is not correct in that way, in general. Yes? So that is why we can actually, this one is a stronger condition because you can swap them. Yes. From here you can swap and then take your definition of continuity. So this one is more or less trivial. So you can call it a love theorem. Yeah, so remember that. So now this one, this is a very good example. This is something that you need to know. Okay. And I have given, because this is somehow not that easy, so I have given you 2 or 3 examples, I think, in the notes. That is enough, so you don't need to be stressed, so you just need to read and learn. So this is a function, f of x equals to x squared, and we want to show, of course, this is a function that is continuous, yes? We know it is continuous. We want to show rigorously it is not uniformly continuous, yes? And you already know intuitively, because that is more or less the graph of y equals to x squared. So we want to prove that this is the case. How should I do that? So 9, 11. So this is 10, 11. So, yeah. So f of x is equal to x squared. We want to show that, of course, f goes from r to r. We want to show that this is not uniformly continuous rigorously. But now you have enough experience. What do you think I will start with? Do you remember this kind of proofs? We want to show it is not uniformly continuous, it is not convergent, something like that. Yes?
We assume that it is, and then show there's a...
Yeah, so proof by contradiction. Yes? So we say that to seek a contradiction, let us assume that f is uniformly continuous. Okay? Okay, but you need to remember the definition. If you believe that this is uniformly continuous, then you have to believe, then it means what? It means there exists a delta such that, I'm just copy and pasting. I have kept this for you. I have started from here, you will see why. So you have already an experience why, okay? So there exists a delta greater than 0 such that for all x and y where in my domain, the domain of my function is R, such that the distance between x and y, this is just the normal Euclidean space. I don't need to write this fancy one. I would write x minus y, the absolute value, is less than delta, then the absolute value between the f's is less than 1. Okay, so you know that this trick, I have some idea about the bad choice for epsilon. And of course, the bad choice for epsilon that gives rise to a contradiction is not evident from the beginning. So you have to do some trial and error. Okay, I hope that this will work if I remember it in my memory. Okay, if it doesn't work and you are in trouble, be careful. You can change it. Okay, so you do some calculations. You see that you do not arrive at a contradiction. It doesn't matter. You just clean it and change it so that it gives you the contradiction. I want you to learn these things. These are not cheating. These are legal ones. Yes, mathematics. Okay, so but this one, instead of writing f of x minus f of y, if you don't mind, let me write it as absolute value of x squared minus y squared, because my function is f of x equals to x squared. So if you tell me, if you insist that this is a uniformly continuous function, then you have to believe that I can find the delta with that property. Yes? Yes? Okay, but can you see the contradiction? You can exactly, this intuition is very, very helpful. So let us do it here. So this is my function x squared, okay? And I know that x minus y is within the threshold of delta, okay? So let us say that this one is delta. I'm just thinking loudly. I want to arrive at a contradiction that the distance between these values is less than 1. It's very clear that it is nonsense, yes? Because if I go to the right, yes, it doesn't matter even if I make them very close, they will become very far apart. So finally, they will go beyond my 1. And if my 1 is bad, I make it 1 over 10, and then it will work. Yes? So there is a clean way of doing that, but that clean way comes after I did this dirty work. And the dirty work is good enough. So you don't need to change it. So can you think about it? So I would say that let us start. What is my goal? I want to come to a contradiction. So I want to to convince you that there is some delta, which is fixed here. And this delta, this is fixed. I cannot tamper with the length, but I can move it around. Okay? So I want to convince you that there is some point that if I move this here, then the distance here will go beyond 1. Is that clear? Okay, so how can I artifact that? For example, I will consider this alpha. Because I want to go to a scratch paper to find something. Then this will be alpha plus delta. Yes? This length will be alpha squared. This length will be alpha plus delta squared. And I want to make this distance bigger than 1 intentionally to arrive to a contradiction. Yes? So let us calculate this distance. This distance is alpha plus delta squared minus alpha. This is this is the dirty work. Okay, so what happens here? This becomes alpha squared minus alpha squared, 2 times alpha delta, and then plus delta squared. Yes? Okay. So I want to make it bigger than 1. Again, remove this idealism, yes? So you want to do simple for you. Do you agree I want to get rid of this delta squared? I can't, because this one is automatically greater than that. Yes? So if my goal is to make this one larger than 1 to arrive to a contradiction, okay? I know this one is equal to this and this one is greater than this one. So if I can manage to make this one greater than 1, then I am done. You have a question you want to answer?
There's no question.
Okay, so what can I do, for example?
1 over delta.
1 over 2 delta, something like that.
Yeah,
so this means that delta should be, so alpha should be picked 1 over 2 delta. Yes, so I get some, so I'm dividing, so I want to make this one greater than 1, so I divide it by 2 delta, because delta is given to me. I am looking for the appropriate alpha. Okay, so I divide by 2 delta, and I get alpha should be greater than 1 over 2 delta. Okay, so which one you choose? For example, I would say that now x is equal to 1 over 2 delta plus delta over 2. Yes? Something greater than 1, but does not go beyond that threshold, because I want to be within the threshold. So one thing I chose this one. The other one, I will choose this one. Yes? Okay, so what I'm saying is, every mathematician writes things clearly, but they don't show you the dirty work. So that is the dirty work. And then you put your suits on and put your tie and then come to a conference and say something. Okay, so what do you say now? So we would say that I claim that this is not true. So I would say let x be equal to 1 over 2 delta plus delta over 2 and y be equal to 1 over delta over 2. Yes? Okay, I want to show you that this is a contradiction. I have to convince you that the numbers I have chosen respects the condition but does not respect the result. Okay, so how should I do that? Let this one and that one. Absolute value of x minus y is equal to absolute value. So it was not easy. I'm just trying to tell you, because if you read the text, math text, they just write these things for you. They don't tell you how to engineer those numbers. But I'm trying to tell you something about how to engineer them. Okay, so then I would say that absolute value of x minus y is equal to this. What is the result? The result is delta over 2, which is less than the delta. So I am respecting your condition. I am not cheating. But then I want to show that this is not correct. Okay, but I calculate this one. X squared minus y squared is equal to absolute value. X is 1 over 2 delta plus delta over 2 to power 2. And then I have minus 1 over 2 delta to power 2. Okay? Let us see what happens. Let us calculate. This 1 to power 2 will cancel this 1 to power 2. This 1 to power 2 is delta squared over 4. 2 times the first one times the second one. It is 1/2. Yes? Am I right? No. Well, yeah, times 2. Everything is right, so I am in trouble now, yes? So I will change this 1, okay? So because this is equal to, do you agree? Are you happy with my calculations? The first one squared will cancel that one.
Yeah.
2, this one squared, I have written it correctly. 2 times the first one, 2's are cancelled, deltas are cancelled, so that's correct.
Yeah.
And then you see that I am in trouble because this is not guaranteed to be greater than 1. Okay? Now I will go and make it. Okay? So this level of cheating is legal. Yes? So then you see that what happens, but this one is greater than 1 over 2. Yes? Is that right? So what I did, I messed up a little bit. Instead of writing it for epsilon equals to 1, now I changed my mind after the calculations. I imagine that I have started with 1 over 4 from the beginning. Yes? So for that 1 over 4, a delta is granted to me. I take your delta. Miraculously, I came up with these two numbers, but I told you how to engineer them. Okay? And then I claim that the numbers I picked using your delta respects your condition, but does not respect this condition. Because when you calculate it, it is greater than 1/2, so it cannot be less than 1 over 4. Is that right? Do you understand what is going on? But this uniform continuity is very nasty for me as well, to fine-tune those numbers. So I have given you some detailed exercises, but try to engineer them yourself first and before looking the problem. And I try to give you the cleanest way. So if you go, my solution for this is not that one. It's much simpler than this one. But it is hard to come up with those guesses, but this engineering tells you how to find them somehow. So I would recommend you learning this method over the clean way. Any questions? Yes?
How will you show that the x squared is continuous? Or can we just assume?
So this is a good question. Why x squared is continuous?
Yeah.
Yes? So first of all, I rely some of your intuition in calculus. So f of x squared is continuous. But if you want to prove this, how you can really prove that f of x is continuous at any point? So you have to use epsilon delta definition. Or we learned something about, if you remember, any point here. So I told you something yesterday, that what we learned about continuity in calculus was more or less correct, except that if you are working with isolated points. So if you are not working with isolated points, so every point here is not an isolated point, because the domain of my function is the set of R. None of the points is isolated point. So if this is not an isolated point, what you learn in the calculus is still valid in this course. So if I want to prove that x squared is continuous, I pick an a in R, and I calculate the limit of x squared, x goes to a, which by the algebra of limits is a squared, and that is exactly f of a. That's the continuity. But if you want a more abstract level, then you have to go with the epsilon delta definition. But you don't have to. Because this mindset you need to have. We start with the abstract definition epsilon delta, but epsilon delta definitions are not very useful in calculations. We use this definition to prove some algebra theorem, and then from that point onward, we use the theorems. Okay? So don't worry about that. Any questions? Let us see if we can. So this is the main theorem that I think that we will done. This is the main theorem I want you to remember. Do you remember? This is one of the functions which is continuous, according to what she asked. It is continuous, but we showed rigorously it is not uniformly continuous. And on the other hand, we learned that continuity implies uniform. So uniform continuity implies continuity. Yes. In this example, we learned that the other way around is not true, because we had a continuous function which was not uniformly continuous. But this is the main theorem of this lesson. The main theorem is that if you have a continuous function on a compact metric space, then it is automatically uniformly continuous there. Okay, so now I want you to see the proof, and then we are done. Because the next theorem I will not prove it, because that's intermediate value theorem, but I have written the proof for you in the notes. So let us try to prove this. It's a beautiful proof, if I can generate it on top of my head. So we have two metric spaces. These are metric spaces, yes? And then what we have a continuous function. This is continuous. And we have one thing more, it's important, is compact. Yes? Then we want to show that the other way around is also true. Okay? So for example, in the exam, I can ask this question. Okay? For example, I can ask, are uniform continuity and continuity equivalent? Okay? If not, for example, explain. Okay? What extra conditions we should add so that uniform continuity implies uniform continuity? It's a knowledge-based question. So then you need to remember, oh, this space should be compact. Yes? So this is something that you need to know. Okay. So how should we prove that? The proof is complicated. I think if I can regenerate it. So where do you start from? We want to show that f is uniformly continuous. So what I should do? I would say that let epsilon be given. Yes, we show that there exists a delta positive such that what? If for every x and y. So if x and y belongs to x and dx x and y is less than delta, then dy f of x and f of y is less than epsilon. This is what we want to show, yes? Okay, so somehow you have an idea. If I want to use this assumption of compactness, I need to have an open cover of my set. But what we say is that the proof is a little bit complicated. Make sure that I'm not lying to you, but don't resist what I am doing, okay? Try to relax and just be careful that I'm not lying, okay? That's enough. So what I'm saying is that let P belongs to X, okay? P belongs to X means, so F is continuous on X, this is the assumption, and I have picked a point there. So this means that F is continuous at P, okay? This means that I can use your epsilon, because be careful, epsilon is given to me and the person who gave the epsilon has left the room. Okay, my duty is to provide him with the delta. Okay, so epsilon has given to me and I know that I picked a point and then I use the epsilon given to me and feed it into this machine. It will generate a delta for me. Okay, do you agree? Because I know F is continuous at P and I have my epsilon in hand, I put it here. So then it means what? Then it means that there exists, I want you to feel it, such that for every x in x, if dx and x and p is less than delta, then the distance is less than epsilon. Okay, what should I write here? You gave me my epsilon, I feed my epsilon to this machine, it gives me a delta. So I would write delta greater than 0. But be careful, this delta depends on what? Of course, it depends to the epsilon, which I don't want to write it because always delta depends on epsilon, but it depends on something more. What is that more? P, very good. And when you want to show that delta depends on P, you put it an index here. So this means that when you give me an epsilon, for every point, I will find a delta that works like this. Yes? Is that right? Okay, now let me write everything. Don't resist. Be careful, I'm not lying. Okay, so I'm writing an index set of families with neighborhoods of these numbers that I get, divide them by 2, okay, and then center at P, and P belongs to X. Can you tell me what is it called in mathematics? What I have written here is what? Is a collection of neighborhoods. Neighborhoods are open. So this is a collection of open sets. But yes?
So it's not an open cover.
It's an open cover for X. Why? Because every point, every neighborhood contains the center. Okay? So this means that every neighborhood at least have one point of X in it, and that is the center. So if I consider all these neighborhoods, it covers my set. Yes? Is an open cover of X. Because every point P is included in the center of the corresponding neighborhood. So if I consider all of them, it's an open cover for X. Yes? But X is compact. So what can I conclude? Just tell me, what can I conclude? This is an open cover for a compact set. It means it has a finite open subcover. Yes? So let me call this U for simplicity of writing. Then it means that U contains a finite subcover for X. Yes? So let me write it down. What does it mean? It means X is a subset of finitely many of them. Let us say n of them. N delta P1 divided by 2 P1 union n delta Pn divided by 2 Pn. Yes? So X can be covered by finitely many of them. Let me call the number finite number n. Yes? That means this. Now, do you remember what you are waiting, what the person is waiting for me? The person is waiting for me to give a delta for him. So now I have my big claim. Yes? Delta is the minimum of these numbers. Yes? So this is the minimum of these numbers. Okay? So do you agree what we are doing? Yes? We were supposed to find that delta that works. Yes? I am claiming that this is the delta that you were looking for, but I have to convince you. Okay? I have to convince you how? I would say I have to convince you that this works. So I would say let x and y belongs to x and dx x and y is less than delta. We show that one. dy f of x and f of y is less than epsilon. Okay, so I okay, so you will see I will be a little bit in trouble. So if you don't mind, let me make it epsilon over 2. Yes, I realize that it should be. It doesn't matter. If you give me epsilon, there will be a delta with epsilon over 2 as well. It's not very important, but you will see why. Okay, so how can I prove this one to you? Okay, so y belongs to x. What does it mean? X is a subset of this one. Y belongs to x means y belongs to this union. So it means y belongs to at least one of them. So this means that there exists an I in the set from 1 to n such that y belongs to n delta pi divided by 2 pi. So then this means that the distance from y to pi is less than delta pi over 2. Yes, that's the meaning of being in the neighborhood. But then this one is definitely less than delta pi as well. Because it is less than delta pi over 2, it is definitely less than delta pi as well. Okay? And, oh, sorry, I made another mistake here. So I put the index here, p, but I forgot to put the index there, okay? Okay, so now I use that star. Okay, so this means that by star, I will have dx, dy, f of y, f of pi is less than delta p, is less than epsilon over 2. Yes, because of this condition, using a star, which is correct for every delta p, including delta pi, I can conclude this. Okay. Okay, one more thing is that now let us consider dx, and I choose x this time with pi. Okay, this one is less than or equal to dx x and y plus dx y and pi. This is also triangle inequality, but then this one is less than. This one is less than delta. This one is less than delta pi over 2. But delta is the minimum of all of them. So this is less than or equal to delta pi over 2 plus delta pi over 2, which is a delta pi. So dx, x, and pi is exactly less than pi. So this means exactly using the star again, I can conclude that dy, f of x and f of pi is less than epsilon over 2. Just 50 seconds. Now my goal was to show this one is less than epsilon. So I would write dy f of x and f of y is less than or equal dy f of x and f of pi plus dy f of pi and f of y. Triangle inequality on the y side. But this one is less than epsilon over 2. This one is also less than epsilon over 2. So I can write this one number 1, this one number 2, number 1 and number 2. But this one is just epsilon. Okay? So we are done. And the reason I changed this to epsilon over 2, because if I didn't, then I will get 2 epsilon at the end. But that was not bad. I mean, 2 epsilon is also good. Okay, so that's a very important theorem. Again, this is, I mean, if you want to learn these things, it is good to know the proofs at least, or at least see them once, but don't worry about the details in the proof review. Any questions? Okay, see you on Friday, I think. Thank you. Thank you.